Hello everyone, welcome back to another A-Star Express video. I'm Srivatsa and today we'll be going through paper 6 of the May-June 2025 series for chemistry. And if you were watching this close to the date that it was uploaded, you probably have your IGCSE Chemistry paper 6 exam in a few days. So this is just to help orient you towards the kind of questions you'll see in the exam and also give you some valuable last minute tips and tricks along the way. Right, so without further ado, let's jump into the questions. Alright, so starting with the first question. So these paper sixes, they just have a very strict pattern about the kind of questions that they usually ask and the order that they ask it in. Right? First they always start with this kind of general experiment that reacts either two compounds or two elements, and then usually they go into titration in some form, followed by qualitative and quantitative analysis and a plan and experiment question. So here we have the very first experiment question, right? It's just a few simple subdivisions that test your knowledge of how experiments are generally supposed to be carried out and how this specific experiment is supposed to be carried out as well. Right? So starting off simple, A. Name the apparatus labeled A in figure 1.1. So this is a gas syringe, right? So you may have probably seen this in the lab, right? If you if you guys have gone recently, I'm guessing since you're doing ATP, you guys haven't, but if you have gone to the lab recently, you would remember seeing this. It's how they collect the gas from these reactions and they store it. Usually this is used to either use that gas for another purpose or to measure the rate of reaction to see how much gas is collected per unit time. Right? You don't really need to know all that for this specific question, but they might ask you questions based on that in other subdivisions or in other papers. So just how the magnesium ribbon should be cleaned before use, right? So again, this is a simple thing, right? Whenever they ask about cleaning a metal, you always say rub with sandpaper. So this is another standard answer. Now, what is the purpose of the mineral wool over here? Right, so it's water and mineral wool. So this is a little less common, but usually when the reaction container is a test tube, this is seen. It is usually because they don't want the water to run along the tube, right? There's a mineral wool just holds on to the water, right? Because the thing is, you want it to react with steam, not the liquid water, right? So that is the purpose. So it is to prevent the water from flowing along the tube to the ribbon, as it must. I like to add a little bit more details in what they explicitly want to make it as clear as possible. With steam only, and I also like to add that that this is because the mineral wool absorbs the water. Alright, so now they want to know where the apparatus should be heated. So you may have gotten a hint from the previous question, right? We have the liquid water right here. We want it to turn to steam. So one of the arrows will be over here in order to turn this into steam. Now, the reaction will be quicker if we also heat the actual magnesium ribbon, which is because the reaction will be taking place over here. So heating over here as well is definitely needed because a higher temperature is a higher rate of reaction, right? So usually for these questions, again, this is a very common question. Usually you just need to look at which of the reactants in the experimental setup require require some heat to function. Like for example, water that needs to either turn into steam, or ice that needs to turn into water, Or in some cases, you just like, look at the actual site of the reaction. It could be like, here only the water was flowing. Sorry, only the water was like, boiled and the steam reacted with magnesium ribbon. In some cases, the magnesium ribbon or the other reactant will also be moving, right? So you must heat it at the exact spot where the reaction will be occurring. So remember that. All right, so let's go to the next one here. So the only liquid product, so there are no liquid products here, right? Magnesium and water, it's just like, magnesium oxide and hydrogen. However, some of the water may remain unreacted with the magnesium ribbon. So it would just be water. And since it's colorless, we have that as proof as well. The gas collected today is not pure hydrogen. Suggest why the gas collected is not pure. So usually this reaction only releases hydrogen, but it's not pure. And why is that? Just like think about all of the conditions that they've given us. And yeah. So the answer specifically here is because there was already air in here, right? So the thing is, since they did not mention that that either like the test tube was completely emptied of all air before the reaction or something like that, we can assume that air was there. Let's see, the test tube contained air before the reaction, and air contains a mixture of various different gases. This pure air is collected in the gas syringe. Right, so you may not need to write this much for one more question, but remember, if you write this, there is no teacher in the world who can make an argument against it. So if you like know the concept clearly, so yeah, do not write anything that's wrong. But if you know the concept clearly of why something is happening instead of just suggesting it, that should give you some extra points, right? Now, don't ensure it is relevant to the question first of all, and ensure that it is correct. But if you are sure of that, then there's no harm in writing a bit more than what, say, the marking scheme might explicitly expect you to. All right, so now, as I said, this is another like titration style. Sorry, no, like not titration style, but um, it is something that involves like multiple experiments. Titration usually involves multiple experiments, but these other reactions as well, where like they're just like changing the volume and like reacting it, and basically they're changing the volume of the reactants across different trials of the reaction, right? So that is like something that you'll be seeing for the second question. You'll definitely be seeing that. So let's take a look at this. Now, what I would suggest you do is do not read this part immediately, right? And because the thing is, without the context of some of the further questions, it may be difficult. What I would suggest you do is you go through some of these, answer maybe some of the simpler questions that don't really require you to fully understand that, and then you come back to this. All right, so this is quite a simple thing, right? They just want us to record the highest temperature that is reached for each of these and the temperature change as well. So let's go one by one. This is 25, we got 26, 27. And so it looks like they're going with 1 decimal place for each of these. So let's just go ahead with that system. Ensure you match the number of significant figures and the decimal places as well. For example, this is 29.0 right here. This is 31.0. So this is quite a simple thing. Just like you just have to look at the number of divisions that they are going with for each thing, and that should help you with that. The key part where they get you is the number of decimal places and the number of significant figures. So 31, 32. This is in between if you look at it correctly. So it'd be 32 point. No, in fact, actually, this is also in between. So keep that in mind as well. It is not always necessarily a whole number that we are dealing with in these cases, right? So here we have 31, 32.5, and this is 35.5 as well over here. Alright, let me go back down here and just write it out. Yeah, so it is 35.5 degree Celsius. Now the temperature changes again. It is quite simple. Yet again, you just have to subtract both of these. Like for example, here we get 4.5. This would be 6.5. Just use your calculator for this. No stress. Just use your calculator and write it down. Right, like we got 6.5 here. This would be 8.0 again, but remember the number of decimal places rules. For this, it's not the significant figures that matters, it is the number of decimal places. You should not change that at all, right? 10.5 and yeah, sorry, this would be 10.5, this is 13.5, right? And here they're also asking about the mass, right? So for this, you have no choice. You're gonna have to go back and look at what they did with the experiment for this additional context. But notice how you were able to do this beforehand as well, right? So yeah, that's just the order that I would suggest it. But to get some more information on this, let's just go and skim through this part of the question as well, right? So yeah, so they are investigating the temperature change, which makes sense. See, like since you did that part of the question, you have a bit more context about what they're speaking about here as well. So this is definitely the kind of water that I would suggest, right? Dissolves in water. So 50 centimeter machine cylinder to pour 40 centimeter distilled water into a 100 centimeter beaker. So they're pouring this distilled water into it. It's maintained at 40 centimeter cube. And the thermometer at 2 continue highest temperature. Okay, so this is a relatively straightforward experiment, right? What they're doing is they're taking some volume of distilled water. Here it's 40, they're reducing it to 30, 25, 20, 15. Adding the same constant amount of anhydrous lithium chloride and stirring it and checking what the temperature change is, right? Easy stuff there. So all of these would be 2.0 because the mass of the lithium chloride itself does not change. Only the volume of distilled water changes because this is the independent variable, right? This is a control variable. So this would all be 2.0s and this would just be the subtraction of both of these. All right, so yes, so complete a suitable scale of the y-axis and plot your results from experiments 1 to 5 on figure 2.1. So they've given us the x-axis already. Based on this, we need to check what the most suitable y-axis would be. So one trick I'll give you here is if you get a suitable y-axis going, the actual plotting at the line of best fit part is quite trivial, right? So you just need to look real hard. Think about what the best y-axis would be. So the rule for this, the only rule that Cambridge will expect you to follow when you do this, is that they don't want you to use a y-axis scale that is too large. Like for example, if the temperature, like the maximum temperature change that we saw was 13.5 over here. But if you make this 0, 5, 10, 20, 25, 30, 35, 40, the actual data doesn't even take up like 3/4 of the y-axis. That's wrong. You cannot do that. So the rule is the vertical like spread of the data needs to take up at least 3/4 of the y-axis at the graph as a whole. That's the one rule. So since we have it at 13.5, what exactly can we do here? We cannot go 1, 2, 3, 4, 5, 6, 7 or anything. However, we can double it, and that should work. We got what? 2, 4, 6, 8, 10, 12, 14. In this way, the y-axis, by going up to 13.5, it does cover most of the graph as well. Now, since we have 2 here, right, let's take a look at the volume of water that they add. So we got 40 here, right? 40 has a change of 4.5. So we go 2, we go 4, then what is the split here? We really need to ensure that you get that right as well. 4.2, 4.4, 4.6, 4.8, 5, 5.2, 5.4, 5.6, 5.8, and 6. So we can take each subdivision to be is equal to 0.2, right? So let us take a look. So we want 4.5. We have 4.2. We have 4.4. 4.5 would be somewhere right here in the middle, right? I'm not able to use the pen to draw here because I'm not trackpad, but on your notebook, or if you have this printed out and are following along with me, you can just mark a point right here and you'll understand, right? Because we got 2, because we set it to be 2 and 4. Ensure you write it over here, by the way. This will be 2, this will be 4, 4.2, 4.4, 4.5, which is the change in temperature, would be right here in the middle, right? And you should just continue that pattern with with everything else. Like for example, we got 30 degrees Celsius with the temperature change of 6.5, right? How do you do 6.5? With 6.5, it's 2, 4, 6. 6.2, 6.4, and 6.5 again right here in between these two. So ensure that you would use the tiny split between the axes as well to really get it accurate. And one other tip I'll just show you. When you plot a point with a dot at any point, ensure you draw a circle around it so that the examiner is clear about the points that you have marked. Right? Don't just leave it at that, because again, like your papers will be scanned and like sent all over the world, right? It's not the physical paper that the examiner is going to be seeing. So especially when using the pencil over the pen for stuff like this, you should ensure that it is dark, and you should ensure that it is as like highlighted as possible. All right, so extrapolate reduce temperature change with experiments repeated with 45 centimeter cube of water instead of 40 centimeter cube. So this is something that you will be able to do once you have actually drawn this line over here, right? I'm guessing it's gonna be like it's gonna be a positive line, like something around. So it will definitely be above 30. No, sorry. It'll be something. It's below 4.5 because this is a negative trajectory, right? We got like what 4.5 over here and then 6.5 over here, right? We have 246, 6.2, 6.4, 6.5. So it'll be so just like draw. So once you draw the best fit line, just like keep extending it until it meets exactly 45. Draw like a dotted line here as well to meet that point, and then just read off that point, right? So the key here is not the value, right? They don't actually care that much about the exact value that they give. The key here is that you show the extrapolation. You need to show a dotted line from here all the way up here. And you must show a dotted line from the end of that line of best fit until it meets that dotted line upward. At that point of intersection, right, is the extrapolated value. You just need to ensure that you give it the unit as well in degree Celsius, right? You don't really need to do anything else. With that, you get all 3 marks. So you just have to show your process elaborately because that's something that they ask explicitly in the question. Alright, so the energy in joules given out when 2 grams of anhydrous lithium chloride dissolves is calculated using the equation shown. Temperature change into 4.2 into volume of water. Results in experiment 5. So we just go up. Check out the temperature change in experiment 5, 35.5 and 22. That is 12.5 degree Celsius. Right? So the answer here that you're gonna want to show is 13.5, which is the temperature change, into 4.2 multiplied by the volume of water in experiment 5, which was 15 centimeter cube. With that, you get 850.5. Like, it would be best if you show it here as well. You get 13.5 as the temperature change multiplied by 4.2 multiplied by 15 is equal to 850.5. Right, you can just write out the whole answer. The significant figure doesn't really matter here. Now they want you to estimate the temperature change in experiment 1 is repeated using 4 grams of anhydrous lithium chloride instead of 2.0 grams. Experiment 1, right now, the temperature change is 4.5, right? So the estimate here would be, since twice the amount is being dissolved, more energy will be released because, first of all, we clearly see that whenever like the concentration of the anhydrous lithium chloride being dissolved, like for example, if the same mass is being dissolved in a smaller volume, the temperature change increases, right? So clearly, if we increase the mass to the same volume, the temperature change will increase as well. It's really the concentration of like the lithium chloride to water ratio that we care about. So we can say that the temperature change will be doubled to 9 degrees Celsius. Right? So just like 9 degrees C right here. Like you can just use this, like the Celsius symbol on your notebook as well. I'm just using a star here. And the reason, right? What is the reason here? It's simple. Just say, you can just say twice as much anhydrous lithium chloride is dissolved. And you clearly see this is exothermic, right? Energy is being given out. That is the reason why we have the temperature increasing. So we have twice as much dissolved, twice as much energy is released, which is why this temperature is also doubling. You would be more accurate if the beaker used it was replaced by a polystyrene cup. So these questions about polystyrene cups are very common and they just have the same answer every time, right? So we just have to say polystyrene is a better insulator than a beaker, so the heat loss to the surroundings will be less, or right, that's it. Just these Just this one line is enough to fetch you 2 marks. It's that simple. This is a standard question, right? So like that's what I was talking about. Sometimes there are these questions that you just have to like memorize the answer to long before you even know what the actual question is, right? I'm telling you, at least one of these questions will be there word for word in your exam as well. Ensure that you are thorough with these common ATP questions. Now explain why using a burette instead of a measuring cylinder is an improvement. Again, this is yet another one of those standard questions. They will ask you this in various forms in every single exam, right? You just have to say a burette is more accurate. That's it. That a measuring cylinder. It's as simple as that. And you can also use this answer if they ask you how they can improve the accuracy of the experiment. You can say use a burette instead of a measuring cylinder. It's like it is just like something that you're gonna have to memorize. The same with a pipette as well. In a water bath is not an improvement. So this, however, requires some degree of higher order thinking. You just have to consider what's happening here. But you should also recall that a water bath is typically used when you want the temperature of something to remain constant. But we do not want it to remain constant here. We want to observe the actual temperature change. So we can say the water bath will keep the temperature of the beaker constant, which is not what we want here. So yes, those are the answers. Remember, these two types of questions, it'll be there in every single exam. Just ensure that you know this, frequently asked set of ATP questions. All right, so moving on to the third question right here. Like a few years ago, this used to be much more difficult because they did not give you these tables at the end, right? Now you have these tests for anions, tests for cations, the gases, and the flame tests. We didn't have this like a few years ago, but with this one, it's now much easier. But that also means since they no longer expect you to memorize it, the like the level of questions that they test is a bit higher. You'll see what I mean here. So first you're telling us what this is: iron, iodide. Iron is the cation, iodine is the anion. So we should remember that when we go back to the table in the back. The student dissolves halogen in water. Yes, aqueous solution, just as we need. Aqueous sodium hydroxide, dropwise and excess. So it's iron 2 plus. Just go here and take a look, right? Not you don't need to do anything else. Aqueous cations, iron 2 plus. Green precipitate, and it is insoluble in excess. But it turns brown near surface on standing. Let's see. We can just say maybe it's green precipitate, right? Let me just ensure that precipitate as a whole, by the way. They don't like it when you use PPT. Precipitate, insoluble, or turns brown on standing. You can just write the whole thing, right? That's not really a problem. But you technically do not need this here, so you can just take insoluble because they only ask excess. To the second portion of this adds 1 centimeter cube of dilute nitric acid, aqueous barium nitrate. So which test is it? It's clearly not a test for cation, it's a test for an anion. Right, dilute nitric acid, then aqueous barium nitrate. That is a test for a sulfate in solution. But is there sulfate in solution? There isn't. There's only an iodide. So we say no change. As simple as that. Right, just compare the test with the table, see if the conditions for the change are met, for the precipitate are met, and answer accordingly. 1 centimeter cube of dilute nitric acid, few drops of aqueous silver nitrate. Remember this test, go back. Which test is it? It is the test for chloride, bromide, and iodide. And indeed, we have iodide over here. So the observation is a yellow precipitate. Just write that. No explanation needed, none of that. Precipitate. Add 1 centimeter cube of aqueous chlorine. Now, which test are they really talking about here? Right, let's just go through the whole thing. Now, there are cases where it isn't actually a test, but they are. It's actually a test that they're giving it in the table, but it is some other reaction that we're dealing with. Right, so let's take a look at like what that could mean here. So here they're testing the halide displacement reaction mechanism, right? Does chlorine displace iodine? You need to think back to the kind of reactivity you see in group 7. Usually this line of thinking isn't seen in ATP, but you never know what you'll get. Yeah, so chlorine is indeed more reactive than iodine, so it can displace it from the reaction to form iron chloride, and just like iodine will be in the solution. When iodine isn't an ion and it is in the solution, it is brown. So we can just say the solution turns brown. So remember this, guys. These halide displacement reactions. Chlorine can displace bromine and iodine. Bromine can also displace iodine. And fluorine can displace chlorine, bromine, and iodine. Right, it's based on the reactivity series, and when the displacement of iodine occurs from a solution where it goes from being an iodide ion to the iodine liquid or gas, it becomes brown. Right, so that's D right here. Now the second part, again, this is always the pattern that they follow. They give a compound and they ask you to write the observations. Here they give a set of observations and they ask you to make the compound. So before you read this, just go through the question and come back to that. About solid K, they made some observations in test 2. What is test 2? So is solid water to form solution K. Solution K is divided into 4 portions. To the first portion of K in a boiling tube, add 1 centimeter cube of aqueous sodium hydroxide, warm the product and hold damp red litmus paper at the mouth of the boiling tube. Now, what is this a test for, actually? It is a test for gas. It is a test for ammonia, where damp red litmus paper turns red. But the damp red litmus paper should turn blue with ammonia, but here it remains red. So we can conclude confidently that the solid does not contain specifically the ammonium ion, because this is a test for ion right here, right? NH3, and for NH3 to be formed as a gas, this compound is what should contain the ammonium ion, but it doesn't. Gas given off in test 3. Effervescence is seen, and yeah. The second way, the boiling tube, 1 hour of sodium, aqueous sodium hydroxide, and a piece of aluminum foil, warm the mixture and test any gas given off. So this is actually a test for something, isn't it? So let's go back to the anions. Aluminum foil, warm carefully. Ammonia is what is produced here. And the damp red litmus paper turns blue as well. So now ammonia is produced once this test is done. So what is the solid K? So from this is a test for a nitrate, right? So nitrate is one of the ions. And if you look at test 1, it is a lilac colored flame, which signals that it is in fact potassium right here. So we have potassium nitrate as the answer based on these, right? We have the fact that, first of all, this confirms it's not the ammonium ion, but this specific test confirms that it is indeed the nitrate ion, and the lilac colored flame confirms that the cation is potassium. So the answer is potassium nitrate. All right, so now on to the final question, right? We have the fourth question here, the plan and experiment question. It's always worth exactly 6 marks. So this can be a bit daunting for some people. Like, you think you're gonna have to write so much and be so detailed, but that's really not necessary, right? You just need to fit the purpose of the question, mention a few apparatus, write 6 clear bulleted points, just needs to be 6 lines max, and you should be good to go. So I will show you guys how, right? So first thing you need to do, of course, read and understand the question completely, right? Usually the experiments here will not be that complicated. It's usually just a few small steps, usually, but it can be more complicated as well in some cases, but usually this is the kind of level we will get, and they should be understandable about what needs to go down for the reaction to actually happen properly. Sorry, for the experiment to go ahead properly. So let's read it. Magnesium sulfate is a salt and it is soluble in water. The solubility of salt is the mass of the salt in grams. It dissolves at 100 centimeter cube at a specified temperature in water at 50 degrees Celsius. Alright, how the solute can be found. Common lab apparatus. Alright, so this is actually quite a simple thing. I'll tell you how you can go ahead with it. They want 100 centimeter cube of water, right? So just say measure 100 centimeter cube of distilled water. Use the exact terminology that they gave in the question. And let's say add it to an evaporating basin, because remember this needs to be heated, right, to 50 degrees Celsius. And use a Bunsen burner. Always ensure you mention the apparatus to heat the distilled water to 50 degrees Celsius. And if we check periodically with a thermometer, right? Saying this additional stuff, it just like adds more value to your answer, and the examiners will love that. Yeah. And then we can say add excess magnesium sulfate, because we want to see how much dissolves, and then we can like take out the rest later to see the difference. Is magnesium sulfate using no, actually first of all we have to transfer the distilled heated water to a conical flask. Ensure that you also keep track of which material you are using, which specific container you are using for the reaction to take place, the reaction container, right? The reactions usually they're not done in the actual evaporating basin, they're usually transferred to a conical flask. That is why I put this here. Now you can say use a spatula. Again, may mention these different apparatus. They may not tell you to do this in the marking scheme, but doing this will definitely add value and will impress the examiner. I'm not saying this will make them overlook other points, but it's always nice to have a good impression, you know. Use spatula to add excess magnesium sulfate to the distilled water in conical flask. And then of course, let's say stir the mixture. Just say it's stir the mixture to ensure that it dissolves. Dissolution occurs, right? Mention that. And filter the solution using filter funnel and filter paper. Sorry, filter funnel apparatus, because that would apparatus, right? And then let's see here. I think I have to collect the residue, wash, collect the residue, and then you have to wash, dry, and weigh the residue as well, right? Now you need to be explicit about this part, about how the solubility can be found. Say the solubility is found. Okay, all right. Let me actually I'm very sorry about this actually. We just need to add one more point here. Hold on. Alright. Just give me 1 second, guys. You can write this at the end as well, but to maintain chronology, you should mention it here. To add excess magnesium sulfate, yes. Magnesium sulfate to a watch glass, actually, and weigh it, right? And then you should add this mass of magnesium sulfate to the distilled water in a conical flask. So the reason to weigh it is because you need it for the calculation. Say, and then just be explicit and mention the solubility of magnesium sulfate can be obtained by subtracting the original mass measured of the magnesium sulfate and the mass of the dry residue, right? So this point gives value to the last part, and all of these, this should be enough to gain you 6 out of 6. The key is to be as detailed as possible, even include details that may not actually be in the marking scheme. A good impression that you know your stuff doesn't hurt, right? But ensure that it does not backfire. If you're not sure about something or some property, do not write it. Now, I'm not saying that you should skip questions, right? Like there's no penalty for guessing. So if you don't know the answer at all, you must write something to like try to get partial credit. But if you already have the answer clearly, but you want to add another point to like embellish your answer or to make it as clear as possible, but you're not sure if that is right or wrong, then you shouldn't add it because that will bring the rest of the answer down as well, right? So yes, so that is how you do this plan and experiment question right here. Alright guys, so that's about it for this paper 6 IGCSE chemistry video. I hope you guys found this useful both in terms of doing this paper and in terms of the general tips that you need for IGCSE chemistry. Don't forget to like and subscribe for more videos in the future, and good luck for your chemistry exam. And once you're done, maybe let me know in the comment section how you guys did. All right? Okay, I'll see you in the next one.